People who study waves extensively in the various fields of physics and engineering are impressed by the similarities which exist in the behavior of waves in various mechanical, electrical, acoustical, and optical wave systems. These similarities are due, of course, to the basic fact that waves of all kinds behave fundamentally alike. These two rib-like structures are mechanical wave demonstration machines. With them, I can show you many of the various wave properties which you may have studied experimentally or theoretically, perhaps without ever having actually seen what the waves themselves are doing. The waves which travel on this machine are really waves of twist or torsion, which propagate along this central wire. Attached to the central wire are these cross arms, which translate the torsional motion of the central wire to the up and down transverse motion of the ends of the cross arms, which you see. The entire structure is supported in a set of bearings which permit the central wire to twist freely. This second wave machine is built similarly to the first. It has cross arms which are considerably shorter than those on the first machine, and as a consequence, the speed of a wave along the second machine is about 3 times faster than the speed of a wave along this machine. You'll see later on why I have these two machines. First, I want to show you the two different ways in which waves may be totally reflected. Observe that right now this machine has a free end. That is, this last cross arm is perfectly free to move without restraint. If I start a wave at this end of the machine, that wave travels down to the far end, is reflected there, and returns as a reflected replica of its original self. But now let me terminate this machine in a different way. I'll clamp this last cross arm to a heavy stand so that a wave arriving here can't produce any displacement of the cross arm. This time you see the wave is reflected upside down. The reflection is still total as it was before, but the wave is inverted upon reflection. In a mechanical wave system, then, there are two ways in which the total reflection of waves may take place. Right side up, if the reflecting end of the medium is completely free, and upside down if the reflecting end is completely restrained. Now, if nature has any consistency, and we like to think she does, this alternative reflection possibility should exist for waves of all kinds, and these other drawings here show that indeed it does. Take the case of an electrical transmission line, for example. You know that there are two ways in which electrical waves can be reflected, depending on whether the far end of the transmission line is terminated by a short circuit or by an open circuit. And similarly, in the case of waves traveling down an acoustic tube, there are two different reflection possibilities, depending on whether the end of the tube is closed by a rigid termination or by the acoustic analog of a free end. Note that in the mechanical situation, a clamp is a constraint preventing the displacement of the end of the wave medium. The electrical analog of this state of affairs is an open circuit termination on the end of a transmission line, preventing the flow of current at such a termination. And the acoustic analog is a rigid closure at the end of an acoustic tube, preventing the longitudinal vibration of the air. In all of these cases, the reflected waves come back upside down, and in all of these other cases, conversely, which are analogous to the case of the free end of a reflecting wave medium, the reflected waves come back right side up. You see, nature really is consistent. Well, now let's have a look at some of the other things we can do with our wave machines. One of the most important topics in